Hello, and welcome to YorkTalks 2022. My name is Mark Post, and I'm at the University of York Department of Electronic Engineering in the Space Robotics and Autonomous Systems Laboratory. My research focuses on robots that can work in harsh and distant environments like outer space or on other planets, and on making them intelligent enough to take care of themselves without human intervention. Today, I want to talk to you about robotic colonization of a dynamic universe. More specifically, I want to talk about the robots that we will need to colonize this universe, with the challenge being the dynamic part. Everything new that we encounter is different, and everything changes over time. My colleagues and I work on developing space robots, rovers for planets, and satellites in orbit and deep space, so that robots can pave the way for humans to eventually colonize other planets. The question is, what do robots need to colonize other planets before we do? We have brains shaped by evolution and individual experience to guide our ventures into space and other uncertain environments, and we can adapt very well to new and unexpected situations. However, we ourselves are relatively fragile and adapted to life on Earth. As toolmakers, we often prefer to explore these dangerous places using machines. This is the Sherpa TT rover developed at DFKI in Germany. It is physically very capable of exploring complex environments, and it can navigate itself and perform basic tasks autonomously. However, robots like this traditionally have neither the experience needed to guide them in their exploration tasks, nor the ability to evolve and adapt to new places and unexpected situations by themselves. Humans, in this case, are too far away to react and respond in time to prevent a collision or to control an interaction with the environment, like picking up a rock, for example. My research focuses on applying probabilistic reasoning, machine learning methods, and intelligence methods that could allow these machines to have some degree of these abilities themselves. Now, the first step in producing intelligent behavior is having enough information from sensors to make decisions and to allow the robot to be aware of its surroundings. In a project called Infuse, we developed what are called data fusion algorithms that combine information from many sensors, such as vision sensors, laser scanners, or LiDAR, position sensors, and so on, into useful information that the robot can use to make decisions. This is a result of what the robot actually sees by fusing and assembling three-dimensional LiDAR data. Most robots are only able to identify what is around them and sense where obstacles are when planning a path to a destination, as they're programmed to. Much of our current research focuses on artificial intelligence, or AI, that allows robots to learn from sensor data like this, or from previous experience while operating. However, this doesn't by itself produce what we would call true intelligence, because it relies on data that we have to provide and classify for the robot. Robots in the future would need to take information like this and interpret how to respond based on only an understanding of what their overall goals are and what's in their surroundings, building a local model of their environment and then reacting based on their own capabilities. The reason for this, of course, is since we're exploring the unknown, we can never program them with enough information to cover every possible eventuality that they will encounter. Now, there's many other reasons why we need to seek something closer to true intelligence for robots. The satellites and spacecraft that we send into orbit and beyond will, in the future, be modular. The picture on the left here shows reconfigurable satellite components that we created in a project called MOSAR, Modular Satellite Assembly and Reconfiguration. Modular spacecraft, like you see on the right, can be constructed of functional modules like these and can be automatically reconfigured to replace damaged hardware and to perform repairs, and also to add new capabilities to the spacecraft. MOSAR also developed a walking manipulator that can move modules anywhere on the exterior of the spacecraft, which allows creative reconfiguration of the spacecraft with a minimum of additional robotic hardware required. This will eventually lower mission costs because we're minimizing the amount of mass we need to launch from our planet to give a spacecraft a certain functionality. However, this also means that we now have a vast number of potential configurations for an equally vast number of missions that the spacecraft could perform autonomously. How can we program a spacecraft to be able to perform all of these potential tasks when it can change its shape and its functions at will? One solution is to be able to make it infer what to do based on knowledge it has of itself and its mission. And this kind of reasoning ability is a major focus of our research at present. Robots will need to be able to reinvent and reshape themselves like these modular satellites, and do so without human intervention. This implies they will need some form of creativity. However, given the high costs of space missions, they'll also have to do so safely and reliably. We inherently desire that they be safe and predictable like computers are supposed to be, but would they really be able to colonize the universe for us then? The problem with AI for robots in space is that a robot that's creative and intelligent will make its own interpretations about reality. It will not necessarily see the world in the same way that you do, and as a result, it will not necessarily agree with you about what to do. This isn't a new problem. Alan Turing, one of the founders of computer science and AI, stated in 1947 that if a machine is expected to be infallible, it cannot also be intelligent. There are several mathematical theorems which say almost exactly that. However, he also said, but these theorems say nothing about how much intelligence may be displayed if a machine makes no pretense at infallibility. We're now creating machines that can make their own decisions, but we aren't sending them into space. Why is this? Well, because we desire infallibility in these machines, because we're putting years of work and millions of pounds of funding into a machine that might not do exactly as you expect once it's in space. If it were a human, would we trust it more? Possibly. But we want to build machines that are perfect so they never make mistakes. Or do they? Consider that Europe's Schiaparelli Mars lander failed to touch down safely on Mars in October 2016 because it rotated fast enough on atmospheric entry to saturate Schiaparelli's spin measurements, which, when combined with radar altitude measurements, resulted in the onboard computer calculating that it was below ground level. The spacecraft then immediately assumed it had already landed, made no attempt to slow down for landing, and crashed. This is a state-of-the-art machine that was designed to make no mistakes. But internally, the machine didn't make any mistake. It simply encountered a situation that it had not been programmed for, and it lacked the intelligence to respond appropriately. Human operators are too remote to respond in time to critical situations like this. And regardless, they're out of contact with a spacecraft during atmospheric entry. This is why robotic intelligence at some level is ultimately and critically needed for the exploration of space. We will have to give up some degree of our perfection in our good old-fashioned Turing logic machines in expected situations to allow the machine to cope with unexpected situations. Will this lead to more successful missions in general? The problem isn't quite that simple, but it is certain that we will need to learn how to trust our creations. Now, traditionally, we trust our own decisions. But if we only do that, this leads to us having to make all the decisions. Ground crews for space missions work around the clock to make these decisions, like the one you see here. But these crews are expensive and labor-intensive to manage. NASA considered ending the highly successful and long-lived Mars exploration rover missions, mainly because of the cost of maintaining the ground crew. And ground crews, of course, are also creative beings with the ability to learn and assume and make mistakes. We're not perfect. So are humans better at space exploration, or are robots better? I don't really think this is the question. After all, we all have our own strengths and weaknesses, but we will undoubtedly need to rely more on robotic intelligence in the future. Overcoming these challenges will require a new paradigm shift in artificial intelligence. The space industry, like most safety-focused industries, is very hesitant to adopt technology that is not completely trusted as of yet. Space systems undergo extensive validation and verification processes to ensure that they do what's expected and that they do it repeatedly and reliably. But we have no way to do this validation and verification for creative systems that might change their answers or their interpretations or encounter unexpected situations like the Schiaparelli lander did. Perhaps we might have to look more at robots in the way that we say trained astronauts, as imperfect entities with high potential. And then how will these robots need to see us? Will they have to respond to our commands without question? Or as creative entities, would they have the ability and the right to question our orders if they're obviously incorrect or dangerous for the current situation? These are ongoing questions about robots on Earth, but for the purposes of space exploration in distant places far away from humans, we perhaps are justified in letting these robots prioritize their own survival. Now, a dynamic universe will require dynamic explorers that prioritize survivability, adaptability, and self-sufficiency. My colleagues and I have developed many new concepts for robots that can accommodate this new paradigm shift in intelligence and exploration, focusing on self-sufficiency, adaptability, and robustness. We've developed self-reconfigurable robotic modules, which you can see on the left here, that can be automatically assembled into many different forms, autonomously reinventing themselves and able to replace faulty components and able to accomplish many different tasks in space and on other planets. A relatively small diversity of modules can produce a vast array of different kinds of robots, as shown in this concept image by Hassel Studio. We will eventually make colonies of robots in space that will prepare and maintain habitats to be used by human colonists. However, the complexity of operating these endlessly changeable robots autonomously will require a completely different approach to design and programming than has been previously used for space robots. We also design robots that are flexible and robust based on tensional integrity or tensegrity principles as shown on the right. These kinds of robots take inspiration from structures in nature, including the spine and the joints of our own bodies, to fold efficiently for transportation through space, to absorb impacts without damage, and to be mobile and harsh in complex terrain. However, they're also very difficult to model and to control as they bend and flex in response to their environment, and they require some measure of intelligence to compensate for this changeability. We envision space explorers of the future as changeable and organic in nature, able to adapt and evolve and survive in extreme and dynamic environments. And for this to be possible, they must be self-sufficient and intelligent to some degree as well. Now, of course, it will take some time for robotic colonization of space to be possible. And we'll have to expend a lot of effort in changing not only the technologies that we use to create robotic space colonies, but also our own perspective about how machines in these colonies are built and operated. We'll need to overcome our mental inertia with the present way of doing things. We will also need to give up some of our valued control over our creations and develop a relationship of trust with our robot companions. This also means that we'll have to bridge somehow the uncanny valley where we feel uncomfortable as humans with these intelligent but not quite human-like robots that may see the world differently from us. And whether we achieve these goals of space exploration and space colonization depends on our dedication and our ability and our willingness to spend the resources required to bring this new paradigm about. Finally, we will need to satisfy ourselves that what we make is suitable for purpose by creating validation and verification metrics that can quantify that our robots are reliable despite potentially being unpredictable. This paradigm shift is a work in progress. Even more than the changes in technologies that can make robotic colonization of space happen, it's our own changes in thinking that will make it happen. And it will happen because it needs to if our robot companions are going to help us colonize the universe. Thank you very much. I'd like to acknowledge support from the German Research Center for Artificial Intelligence in Germany, Space Applications Services in Belgium, Hassel Studio, and as well as the European Commission and the Horizon 2020 Perispera project, and funding from the EPSRC.